Now that we know a bunch about similar triangles and similar polygons in general, and also how the elements of proportionality kind of show up within them, we're going to discuss some more theorems about proportionality in general. Some of them will have to do with similar triangles, some will just have to do with triangles in general, and some will just be theorems about proportionality regardless of whether or not a triangle is involved. So, I'm going to throw some theorems at you, and they're going to be confusing at first because they're just going to be words. But then once we put some diagrams to them, it'll make a lot more sense. So the first two theorems go together because I have a theorem and then I have the converse of it as well. And so the first one, the triangle proportionality theorem, says that if a line parallel to one side of a triangle intersects the other two sides, then it divides the two sides proportionally. So to really get an idea of what's going on here, I probably need to look at a triangle. So let me go ahead and do that first. So if I have, this is a pretty good triangle. If I have a triangle here, and if a line parallel to one side of the triangle then intersects the other two. So I'm going to pick side AC here, and I'm going to draw in a new segment that is parallel to it, but then intersects both of the other sides. So I'll give those points names. This will be E and F. And it says then that it divides the two sides proportionally. So in other words, I'm going to give these some variable names. Actually, I won't. I'll just leave it how it is. AE is proportional to CF in the same way that EB is proportional to FB. Is one of the ways of looking at this. One of the great things about these problems is that, when one thing or one set of things is proportional, there's pretty much no way of going wrong. Like all the things are proportional. So what I'm saying here is that AE is to CF in the same way that EB is to FB. So in other words, these sides that are across from each other are proportional to each other in the same way as these sides are. So these ratios are the same because they're being divided by these parallel lines. That is one way of looking at this. The other way of looking at this is by talking about how it divides these sides. So AE is to EB in the same way that CF is to FB. So my sides are proportional, or rather they are cut proportionally to each other. The ratio between AE and EB is the same as the ratio between CF and FB. And all this kind of makes sense because you can see the similar triangles that exist in here, right? I've got my large triangle here, ABC, and then I got my smaller portion here, EFB. They're similar to each other because they obviously share this angle, and then I've got parallel lines, so I've got angle going on here. And so what that means is that these two triangles are proportional to each other. So, similar to each other. So we also know, another way of looking at the same thing is that EB is to AB in the same way that FB is to CB. And because of that, when I divide these into their portions, they're also going to be proportional to each other. So there's just a whole bunch of ratios that are going on here. They're all going to be equal. And so as long as I'm pairing things up properly, then I'm going to be good. And so it's all about finding these pairs. AE is to the thing across to it, CF, as EB is to the thing across to it, FB. AE is to the side or the length on the same side, EB, as CF is to the length on the same side, FB. So as long as I'm matching all these things up, I have a couple sets of proportions here. And the reason that this works out is because these are obviously the same statement. If I were to switch, for example, AE and FB, what I would get is this same ratio or same proportion down here. So that is the triangle proportionality theorem, but the converse of this is also true. So if I were to go the other way around, so if I were to start off with these triangles and not knowing that these two lines are parallel to each other, if the sides are divided proportionally, then AC and EF have to be parallel to each other. So the converse of this is just also true. 9 times out of 10 we'll be using this one. but this could obviously come up as well. And so we can move in either direction. Now, one thing that that may have been jogged in your memory here is that we've seen something very similar to this before. We've actually seen a specific case, which is the mid-segment theorem. So we've seen this before in the mid-segment theorem. The mid-segment theorem is actually just a specific example. Whenever this side here connects two midpoints, so if E and F were to be midpoints of these two sides of the triangle, I would divide these two portions, or rather I divide AB and CB in half, and what I would have would be two similar triangles, one who's just half the size or 1/2 scale factor of the other one. So we've seen this before in the mid-segment theorem. Now we're just broadening this to more cases, more ratios. Okay, so that's a triangle proportionality theorem and its converse. And we could actually take an even more general view of the same thing by talking about this other theorem. We don't have a name for it, but it says that if three parallel lines intersect two transversals, then they divide the transversals proportionally. So again, I need a diagram really to kind of figure this out. So if I have three lines that are parallel, we'll space them out at different intervals. If I have three lines that are parallel to each other, I'll mark them all as parallel, and they intersect two transversals. So here's one transversal, and how about here's another transversal. What will be the case is that they will divide these transversals proportionally. So let me label these points then. So if I call this A, B, C, D, E, and F, these parallel lines will divide the transversals proportionally. And so what I mean by that is that I can write proportions again. You can see that the distance from A to C is less than the different distance from B to D, obviously, because I have this more of a slant here. And the more level of a line that I would have cross here, the longer it would be. But on top of that, so is DF to CE. DF is going to be longer than CE in the same proportion that BD is to AC. So let me go ahead and write that out. So AC is to BD in the same way that CE is to DF. Okay, so these portions are proportional to each other. These ratios have the same value. AC is to BD as CE is to DF. And on top of that, just like before, I can talk about these pairs as well. And this is really what the theorem is actually getting at, is more this next statement here, but divides it proportionally. So AC is to CE, AC is to CE, in the same way that BD is to DF. BD is to DF. Okay, so these pairs are also going to have the same ratio. And on top of that, we could actually take this one step further, is not only are we looking at these pairs here in between AC and BD and then between CE and DF, but I can also talk about the pair of how AC is to BD. Actually, let me use a different color. AC is to BD in the same way as so I've been talking about kind of using this first line and the second line in comparison with the second line and the third line, but I could also talk about the first to the second, so AC to BD, in the same way that I talk about this entire thing. AE is to BF. And so there's just so many proportions that I can set up here because everything is being divided proportionally by these parallel lines. Now, the reason that I said this is just a special case, or actually this is a more general case of what we were just talking about, well, let me draw this again. So in this situation, we have two lines that will end up intersecting, somewhere up here. But what I could also talk about this is, what if I had a situation like this? So my previous theorems about triangles, are really just special cases of this theorem here. Because what if my two lines here all intersect at the same point, or they're concurrent with each other? Then what I have is a triangle that's divided in the same way that we just talked about previously in the previous theorem. So this theorem here about parallel lines is really just a more general case of the one before. So we could obviously do this with more lines. I could have 5 or 6 lines that are parallel, and everything is still going to be proportional to each other in the same way. So that was theorem number 3, and I have one more that I want to talk about, and this has this is kind of the odd one out. I feel like it's still going to divide things proportionally, but just kind of in a little bit different way. So it says that if a ray bisects an angle of a triangle, then it divides the opposite side into segments whose lengths are proportional to the lengths of the other two sides. Okay, so what does that mean? Let's go ahead and draw a triangle. So if I have a triangle, and we'll name some points, A, B, and C. All right, so if a ray bisects an angle of a triangle, so let me try and bisect this angle here, something like this, okay? So if a ray bisects an angle of a triangle, so these are congruent to each other, then it divides the opposite side into segments whose lengths are proportional to the lengths of the other two sides. Okay, so what I'm saying is the longer that this side is, AC down here, the longer that DC will be as well. So you can imagine if I extend this out, so if I extend this out some, what will happen here is that the longer that AC gets, the longer that DC is going to be. Now, BD grows as well, of course, but DC is just growing at such a much faster rate because it's on this longer side. So here's the proportion that I'm trying to set up. It says that AB is to BD in the same way that AC, the side of the triangle, is to DC, the part that's being divided. Okay, so AB is to BD in the same way that AC is to DC. And again, that's just one way of looking at this problem. I can also talk about, so actually let me draw that in. So this one was me saying that AB is to BD in the same way that AC is to CD. But I can also say that AB is to AC, so the two sides are proportional to each other in the same way that the side that's being divided is proportional to, the two parts are proportional to each other. So BD is to DC. So these things here. Okay. So this is just a situation that importantly only occurs whenever this is a bisector. Okay, so whenever I have a ray that bisects an angle of a triangle, then it will divide the opposite side proportional to the lengths of the two adjacent sides. Okay, and then I can set that proportion up in 2 different ways, just like I have been doing. So this was a lot of theorems about proportionality. There's a lot going on here. But I think once you get kind of into it and start using it a little bit more, it's intuitive. Because really I'm just trying to match up like parts. Okay? If I'm going to match up the two sides of this triangle here, I'm going to match them up in that ratio. So AB is to AC in the same way, in the same order that I'm matching up these two sides that are being divided. BC is to DC. And just like in my previous ones as well, I was finding pairs of sides. All the ratios would be the same. All the pairs of sides would be proportional. So, yeah, it was a lot of theorems. There is a lot going on. But these are going to help us solve a lot of problems moving forward.